So, thanks for giving me the opportunity to be here speaking today. My presentation comes right after the one of Yuan, and I will talk more about, generally about the pipeline that we are developing in order to handle Illumina X Ten data. This is this new incredible machine by Illumina, and also all the other samples that we produce every day in the last 2-3 years. So I work at SciLifeLab Stockholm on the National Genomic Infrastructure. This is Uppsala, here where we are, and Stockholm plus Uppsala form the NGI node. There are two facilities, one here and one here, that have mainly only Illumina sequencers. All the computation that we do is done, almost all that we do is done on UMAX. So it's a really large infrastructure. We are really a lot of people working in the lab and working as bioinformaticians. So this is our current Illumina fleet, all of it, Stockholm, Uppsala. There might be some changes, I'm sure of it. But as you can see, we claim to be one of the best free equipped labs in Europe. This one in particular is the latest acquisition that we've done, the Isaac X. For now we have half of it, 3 already installed and running in Stockholm, and 2 already installed and running in Uppsala. And pretty soon we will have the other 5 up and running. So some more words about the X Ten system. This is the first system that is able to run to deliver the 1000 genome. So it means that we can sequence a 30x equivalent of a human genome for almost $1,000. Each run of one of these machines produce roughly 1.2 terabytes, corresponding to 16 human equivalents. One run lasts only 3 days. Due to this power, we are for the first time able to do population scale genomics. And in Sweden, there is a lot of effort now to give to researchers tools and ways to access to these machines. And there are being already one call, and one will soon start. Next, in 2 weeks, will be announced for a reference variation database, and also for whole human genome at half of this price. So really an incredible an incredible opportunity for Swedish scientists. So what will change using this machine? This is Stockholm picture, but I'm pretty sure that it's pretty equivalent for Uppsala also. So this is the current production in Stockholm for what concerns samples production. These are the different kind of services that we offer, samples that we produce. As you can see, the bulk of our data production currently is RNA-seq data. We produce roughly 3,300 samples per year that are RNA-seq samples. Our goal is for 2015 to produce at least 2,500 whole human genome samples. This is for the Stockholm side. In 2016, we want to produce at least 5,000 whole human genome samples. This means that next year, this picture, this chart here, will be totally reshaped from one year to another. It's a really huge undertaking for us. Also, this is our current delivery time from when the sample arrives in the lab to when we are able to deliver our user the analyzed data. As you can see, there is a huge variation. Around 40–50% of the time we are able to deliver data in 6 weeks. That is pretty okay in many applications because you have 3–4 days for do lab stuff, then you have incubation times, then you have to wait more. But when you are running an X Ten fabric, as Illumina calls this kind of system, your time gets really reduced. So you have one day for sample QC, you want to prepare the libraries overnight, you sequence in 3 days, and you want to analyze the data in less than 3 days. So this means that we need to have a turnaround for our samples that will be less than 2 weeks, 1 week and a half. It's a huge change. That's the time for my slide about our data production. Also, this is made on real data produced in Stockholm. And I went a bit further than Yuan, so what I've tried to do here is to foresee our production in January if we are running X10 at 60% of the maximum production. So it's conservative. I'm not trying to push it too much. So this is 5 instruments run at 60% of their maximum capacity. As you can see, it's a huge change. Also, this changed the way in which we store data, for how long we can store data. Up to now, we have practically never deleted data because we had enough space. Now things are changing radically. Another huge effort that we have to undertake is the fact that we are 2 nodes. Yes, we are a single infrastructure, but we are split in 2 nodes. And this sounds kind of why we are overcomplicating the things, but I think that this puts us in a really great light, because this will happen often and often, I think, that different sites have to collaborate with each other and running the same pipelines, running the same tools. So what we have to do, we need to have a way to coordinate ourselves, Uppsala and Stockholm, in order to be sure that for the final user, the analysis that we run are transparent. The user has not to know if we are running the sample in Uppsala or in Stockholm. And in the future, we have to envision a place where will be transparent for all users in the world where they have run their data, in China, in the US, or in Europe. The same analysis, the same pipeline needs to be run in order to allow also data spread. So how we envision a sample able to cope with the 10K human genome samples that we are able to produce with the X10, plus the usual 15K samples that we produce every year that are other applications. So a pipeline needs to have all these really important features. It must be highly automated, maintainable, fault tolerant, site agnostic. And this schema represents what we are implementing right now. This is really a work in progress. There are mainly 4 elements in this picture, it really is close to what Yuan has described and what Luca has talked about this morning. And that's really reassuring. It means that we are doing the correct thing. So the first point is the trigger. That's the automatic part of the pipeline. The pipeline is waiting for data, the data arrives, and automatically starts to process the data in several stages. The helper is a part of the pipeline, and it's the manual part, is the diagnostic part, or the part that you use, the commands that you use when something goes wrong. You can pretend that always your pipeline is able to automatically process the data. But at least 80% of the time this has to happen. In the remaining 20%, you need diagnostic tools, you need tools that are able to interact with the pipeline and to restart it, to deliver data, and so on. What the trigger has to do mainly is to put the data in a shape that you're able to use it, and this is really site dependent. And then it has to start an engine. And the engine is what is often called, in an abused way, pipeline. In reality, it's more a workflow. So it's a way to start a series of tools, one after the other, and go from FASTQ files down to important data, VCF files, for example. Yeah, there is also a database, and why this is really important, because in order to coordinate all this infrastructure, you need a way to know what is happening to your data, at what stage in analysis your data is. Otherwise, you have no way to coordinate it. You have no way to know what is coming. You have no way to foresee what is going to happen, and you have you're not able to understand if your data is stuck, for example, in some analysis or in some loop. So this is the trigger, the automatic part. We envision the trigger to start right away when the data starts to flow from the instrument. So Caron is we really like myths. So Caron, in Stockholm at least, mirrors the samples that are loaded into our LIMS system. And so what means is that at every point, Carol knows what samples are going to the instrument. At this point, data flows from the instrument to a local NAS to store the data. And in the moment in which the first data is produced, we start to store it in the long-term storage, as web store. At the same time, also we store it on NAS, and we transfer it through a continuous service, a preprocessing tool. We transfer it to a preprocessing server, like they do it here in Uppsala. Once the transfer is done on preprocessing server, we start the multiplexing. We turn BCL files into FASTQ. Once this is done and everything goes well, we transfer data to UMAX, where we start the pipeline. For now, we are concentrating on the whole genome shotgun pipeline that will be implemented into Piper. But we envision to use this model for all the kind of analysis that we can run. So this is the current status of our implementation. The things that are ticked here, they are done. We are lagging behind here. There is really a lot of work. It's really difficult because this component is really, really complex. Why so complex? Well, because you have to think about all the logic. When the new data arrives, which engine you want to start, how you start it, with which options you want logging, you want to be able to handle errors, exceptions. So you want to automate as much as possible. Here, these lines are the automated ones. The dot ones instead are the ones that we envision will be always manual steps, like generating reports. Mainly report generation, as you have to look at the data before delivering it to the user. It's always better to generate it manually, so you oblige the bioinformatician to look visually at the data. In reality, this is a really oversimplification. The reality is this, and it's much, much more complex than this. This is the reason why it's taking so long for us to implement. On the engine side, for now we have implemented one solution, that is the BWA plus GTK pipeline. This is implemented into a workflow that is called Piper. That Yuan is the main developer, and you will learn more about it in the tutorial of tomorrow. Roughly, this pipeline takes 2.5 days to run on a 30x human genome sample. And what we envision is that we have to bring the analysis from FASTQ generation down to VCF for each single sample. And then this will allow researchers to start directly on the important questions. So what we want to provide for researchers is to avoid them redoing alignment and variant calling, because that are easy tasks. And we have to be the ones that do them and allow researchers, clinicians, to start directly from important questions, not lose time in alignment, data integration, and in variant calling. This is a more in-depth look at what the NGI pipeline does, the engine, Piper. Where we are concentrating our effort now is from inter realignment down to variant quality and recalibration, as here is where we can try to insert as much as parallelization as possible. Right now we are using GTK in a pretty standard way. What we want to do in order to reduce the running time is to parallelize as much as possible. And in this process, we really found lots of trouble. So, for example, the first version of Piper, it was heavily using the file system. So it was running on the nodes as parallel as possible, assessing the file system all the time. And this caused almost immediately the file system to go down, because there were too many assets. So the first thing that we had to do has been to switch to a single node running using the Scratch, the local disk, as the file system was unable to cope with the amount of data generated by the X Ten system. This slide is mainly going to stress the incredible high numbers that we are seeing. A 30x human genome is roughly 80 gigabits per at FASTQ level. When we align, we obtain 180 bytes. Sorry. VCF file is much smaller. We hope in the future to be able to deliver to our user only this. But to do this, we need to convince our users that we are doing a great job, and we are. And the whole process right now takes roughly 55 hours. If we think that we can start 160 genome per start, when we will have 10, the whole X Ten system, it means that if we run 1 genome per node, we need a cluster with at least 160 nodes to reach these numbers and to be able to scale. So, and the amount of data that we'll produce will be really, really high, 42 terabytes at each start. This means every 3 days. So, where we are right now, because the reason of this is to show that we are sequencing really fast and things are happening even faster. So we started the development of the pipeline around March 2014 when there was no really idea that we were going to buy the X Ten. And at some point during August, we discovered that, yeah, you're going to get an X Ten, great. And we have to switch our pipeline from being able to process 500 genomes per year to 5,000 genomes per year, from almost one day to another. And from this time on, things had happened even quicker and quicker. So we have received in November the X Ten. We were able to install it before December. And before Christmas, we were able to deliver already data to the users. And we plan to sequence the first 1,000 genomes already early in 2015, because it's really only a matter to start using these instruments. Clearly, all this pipeline, all this project, it's not possible if it's not done by a big and great team. So I want to thank all the participants. Many of them are here today. As a conclusions, I want to stress the fact that when pipelines get so complex, you need a lot of engineering around them. We need pipeline engineering. We need heterogeneous teams formed by bioinformaticians, computer science, system administrators, and also lab people that interact with each other and are able to understand what's going on in the lab, how data flows, and how we can solve problems. Bioinformaticians alone, computer science alone are not able to solve all the problems. It looks like that bioinformatics is becoming the real bottleneck. Data, it's really easy to produce data, but data itself has not great value. Data has value only if it is processed bioinformatically. And here is where we are seeing the big bottleneck, where we need a lot of new tools, a lot of new ways to work. What we are facing also with the respect of human whole genome sequencing is data integrity and privacy. It's a really big problem, because thinking about a system that is able to work on all the data, it's kind of easy, but when you start to think about a secure system with double authentication, with other kind of security systems, automatization gets really difficult. And a thing that I think that it's really needed is we have to stop to call these things pipelines, because they are much complex. Pipeline is a really reductive term. As we saw, we are planning a system that has a database, it has different tools, it connects, interacts with different entities. It's not a pipeline, it's a really workflow. They are really complex things. So I think that pipeline is too reductive as term. So thanks, and if you have questions.
Yeah, I have two questions.
Have you investigated these reference-based sequence compression algorithms to sort of reduce and avoid storing fast-queued visit files?
Like CRUM, you mean?
Yeah, for instance.
Yes, and that's a problem. We're discussing this at lunch. And the problem about these new formats that came out is convincing people, convincing PIs and researchers that they are good for them. They think that they have to start from FASTQ, and if they don't have the FASTQ, they are not happy. We cannot deliver only BAM files, because if we deliver only BAM files, they will complain, saying, well, I want also the FASTQ. Why? You have already the BAM file. No, they want the FASTQ. Maybe they don't use it, but they want it. So yeah, GRAM is a great thing. We need to see if it will enter in the community, if the community will start to use it. I really hope so.
Okay. Yes. I have a question about the kind of cost of storage, almost the amount of data now in a year. So how does that shift the kind of cost of sequencing? Is the cost of storage now a major issue? It's a major issue.
I think that Ulla has a much better idea than me. In our view, NGI, data storage is for free. We don't really care. So
yeah,
we put their data. We put their data. Then we know that it's not like that. But it's for us, unfortunately, it's transparent. Like resource usage for us is for free. We don't feel that we are paying for them, and also our users don't feel it.
I think a short comment would be when we calculated how much it would cost in that respect was about I think 10%. Around those lines. So
only
for $1,000 genome, it would be like 100. But these are estimates because we still haven't really run these numbers. We have a quick. Did you have a quick question?
So I agree with you that we should call it workflows, and I wanted to know what is the role of your LIMS in the workflow? Is it just to know which samples you have to process?
Yes.
Do you feed back information to LIMS and you can...
There is only one exception right now. We feed back information about the multiplex counts, because the problem is that LIMS often, they are really great for the lab, but they are really difficult to interact. So what we prefer to do is to extract the information, put them in a database, and then display it with a web-based interface. It's much easier for us. Go inside the LIMS and interact with their database. Often you can't, you have only an API maybe to interact with them. It's really difficult. We have one exception that if we sequence a sample several times, we have a script inside the LIMS that sum the number of reads sequenced for that sample. But that's the only exception, and it was really difficult to do it. So I don't think that we will push a lot of information inside the LIMS.
Really, the last question.
Yeah, so you're not an archival facility, you're a data producer, right? So you're delivering results to customers. So it's fair to say that the storage is in fact free for you. But in the long term, it needs to go on the archive somewhere, and I don't think there is an archive for sensitive data thus far in the Nordics, as far as I know.
I think it's on the to-do list of the next cluster and on the big grant.
This is something that has to be really nailed down this year. Thanks a lot.
Thank you to you.
Excellent.